Hello everybody, thank you for joining me, Root Beer here, and we're going to be looking at the very last question. We're going to be finishing off the 2006 Fermat paper. Okay, so this should be the hardest question, so I've set aside some time. Let's take a look at this question in detail. Three identical cones each have a radius of 50 and a height of 120. Okay. The cones are placed so that their circular bases are touching each other. That's kind of hard to see from the picture, and makes me think we might need to draw a top-down view just to understand how the cones are touching. A sphere is placed so that it rests in the space created by the three cones as shown. Okay. So this sphere will come into contact with the cones, and since they're identical cones, it'll all be sort of the same height, and it'll be a symmetric image, basically. In fact, the cones should form an equilateral triangle with their bases. Just trying to get an understanding of the three-dimensional arrangement here. So the rest in the space as shown. If the top of the sphere is level with the tops of the cones, then the radius of the sphere is closest to. Okay, so I'm not the best with the three-dimensional geometry questions, but I find that with ones like this, when it's in the 24 or the 25, probably the best thing to do is not view it as a three-dimensional picture, but to understand, one, the connections. So all these things are tangent to each other. They just come in and touch. There's no overlap. It's not like cubes smushed together. So understand where the points of tangency lie is a very good thing. So there's points of tangency with the cone bases. That's something we should explore. There's also the tangency of the sphere resting inside the cones. And since the cones are identical, that'll occur at sort of the same height. We can sort of slice through and take a look at the big sphere, and then around are sort of the little cones. So I don't want to view it three-dimensionally. I want to figure out where the tangent points are, and then what I want to do is sort of draw two-dimensional pictures that help me understand. If I slice a cone, it's going to be a circle if I'm looking down, or it's going to look like a triangle if I slice it vertically. Sphere, no matter how I slice it, it's going to be circles. So I want to get two-dimensional pictures involving circles and triangles that I can manipulate. Okay. I'm going to do a couple top-down views, and we'll see where we go from there. We'll also probably have a side view. So just what I'm thinking here, I'm not going to look at all the cones, but having a single cone and its side view as to how the sphere just sort of comes in and touches it. We'll draw it a little better. I'll draw the circle first, really. So the sphere from a side looks like a circle, and then the cone sort of comes in here. We know the tops have to be the same. But looking at things from a side view, what can we see? Well, we know the height here is 120, and we know the radius here is 50. 50 here. We've also got this wonderful point of tangency. Now, whenever I have a point of tangency in a circle, I always make sure to connect it up with its radius, so we get an R here. And since the tops are important, I'm also going to bring an R up here. And we know the tops have to sort of be level. And so that imaginary top tangent line also gets a right angle. So you can see I'm slowly making a nice looking picture. And actually, something I've just noticed, these blue lines here, thanks to some nice symmetry properties from the circle, these blue lines are going to have to be the same length. So the distance between the center of the sphere and the center line of the cone is this line here. That's going to have to be the same distance that we go up in slope here. And this actually has a nice little right angle triangle that's in the same ratios. And now that I think about that, I realize, hey, the triangle, the side triangles, the 50 and 120, that has a nice relationship too. it wasn't immediately obvious because it was 50 and 120, but that's a 5, 12 right angle triangle. 5, 12, 13 on the hypotenuse. Okay? So we're making connections, and that's fantastic. So this guy here will be it won't necessarily be 5, 12, and 13 itself, but it will be a similar triangle to the bigger one. And it's 5 to 12 to 13. In fact, I know that the slope of the whole cone is 130. And look at that, I've just drawn one picture. That's all I've got so far, one picture. So, I don't think this is enough information yet. Add in that dashed line. But that's just from one picture. Now, we also have the bases of the cones coming together. I don't expect to get a whole lot of information out of this one. But this is the bases of my cones, and I've used, red for parts of the cone. What I can do is I can connect all these up, and we're going to get 50 for that radius, 50 for that radius, 50 for that radius, 50 for that. We're going to get an equilateral triangle of side length 100 down here. Now, how is this particularly helpful? Well, where is it? We'll use green. The center of this equilateral triangle is going to be directly below the sphere. So we could even draw it here. It's I mean, my picture sort of has them touching. We'll put a little bit of separation there. But that green line on this top-down picture is the exact same. It is just this green dot, but it runs right through the middle of the sphere. So if I imagine my sphere in the very faint yellow, this is my sphere, we've got sort of this side view for our picture here. Now, it's an equilateral triangle, so I can actually figure out the distance from one of the vertices to the center. And that would tell me this overall distance. And that might in some way be, that'll tell me this length here, which will tell me this length here, which will tell me this height here, and this length here, because of the 13, 12, and 5 triangle. I'm not seeing that immediately getting me R, but I think we're close. If I redraw this picture again, a little bit bigger, and yeah, I've lost my point of tangency, so we'll redraw that. I think we're close. I'll just redraw my picture a little bit. Nice green line goes down through here. This blue line and this blue line are the same. And then got a nice little right angle radius here, right angle here. These R's are the same. Now, this this R value, this angle here and this double angle here, this angle here, this angle here. So it'll be another 5, 12, 13 triangle. So I can get this length here, that in terms of R, that plus this 1 R should be equal to this height that I do know. Okay, I've got a plan of attack. I need to figure out the distance from the center of one of the cones to the line going through the center of the sphere. From there, I can figure out the blue line. From the blue line, I can get the hypotenuse when it lies on the cone. From there I can get the height, and then I can also get, and then I can approach and get an equation in R, but I don't want to get ahead of myself. Okay, so vertex of an equilateral triangle of side length 100 to the center of that. That's what we need. Okay. So we'll use probably some trig or something like that. Now the center, that's what we need. I believe it's 2/3 the height, but another way we could do that is it's 120 degrees here. It's the same distance to either side, and we know this is 100, so we can just use cosine law, what I think would be the easiest way to explain this. So x squared plus x squared minus 2xx cos of 120 degrees. Cosine of 120 degrees is negative 1/2, so that and that will cancel out and we'll get a plus. So we'll get 3x squared is equal to 100 squared, or 100 is equal to root 3x. So x is 100 over root 3. Incidentally, what is the height here? The height, it's a 30, 60, 90 triangle, so it'd be 50 root 3 is the height. So this really is 2/3 the height, as I thought. Okay. So this is distance from center of cone to the line through the center of the sphere. Okay. And that would be this blue length right here. So now I know that this is 100 over root 3, and that means this is 100 over root 3 because we've got circles, lines, tangent lines coming from the same point are equal in length. Nice little circle geometry there. So now, and we're going to have to flip the page, so we just remember 100 root 3, that's really the only thing we've worked out here. And I think we are now entirely just with this picture here. Okay, so we have tangent line, and that's the same as this to the center here. So that's 100 over root 3. That's the same as this length here, and now we have, because it's similar triangles, a 5 to 12 to 13 ratio. So I'm going to call it 5, I don't know, I used x, so we'll call it y. So we have 100 over root 3 is 13y, 12y is that height, 5y is there. So y is equal to 100 over 13 root 3. And now the height here, we've got 1200 over 13 root 3. And we've also got a base here of 500 over 13 root 3. I can see why we're going to have to round. They did, in the question, they did say sphere is closest to. So also when I read that, instinctively reaching for my calculator. Okay, so we understand this triangle fully. Now, and I keep drawing too small a picture, so I'm going to draw it even bigger, and I'm going to draw a better sphere than that. Better circle, I guess. No, I want it bigger. I want it really ridiculously big. Alright, that's going to be good enough. Okay. So we've got our precious blue line. And then we have the point of contact here. And I guess I've been using red, so we'll use red for that inner triangle. But what I'm going to do is I've got another, so I can keep extending this over to our center line. And this is also 100 over root 3. 100 over root 3. Now we connect this up. We've got r here and r here. But it's 90 degrees here. And I know that this is checked, this is x. Well, then this is going to have to be checked as well, because checked plus x is 90 degrees, and we've got a full line here. And because we've got all these other right angles, we're going to get a right angle here. So this is x. So this here is a 5z, 12z, 13z triangle. But I can figure out this 12z. I mean, we've got 5y here, but 12z is going to be this full distance, 100 over root 3, minus 5y. So that's 100 over root 3 minus 500 over 13 root 3. So that's going to be 1300 over 13 root 3 minus 500 over 13 root 3. And that will be 800 over 13 root 3. And that's equal to 12z. So now z is equal to, I can divide 800 by 4 to get 200, and then we'll be left with a 3. So 200 over 39 root 3. And r is 13 times z. So it's 2600 over 39 root 3, but the 13 and the 13 will cancel, so it'll be 200 over 3 root 3. That's what I'm saying r is, and I'm hoping that that will be one of the answers. We're going to get our calculator out now to check. So 200 divided by 3, 66, and divided by root 3, 38.49. I'm going to round that to, and it's followed by 2 zeros, so I'm going to round that to 38.5, because I remember the answers had only one decimal place. So this is around 38.5. And that was, I hope, one of the answers. It's D. Okay. So we're looking good. We get our answer of D. I actually didn't expect it to solve it from this equilateral triangle. I was expecting to get this in terms of r, add it to this r, and have that be equal to the 12y here, which I already calculated. But it just popped out right there and quite immediately. Not bad at all. I liked it. We had to use some circle geometry, some similar triangles. We even had to understand how equilateral triangles work in the distance between their centers and the corners. I think that was a very nice question. It really had a lot of things coming together for it, and that's what makes a good question 25. A mastery of a lot of different types of math. In this case, a lot of different aspects of geometry. Circle geometry, similar triangles, equilateral triangles. Fantastic. So that's going to wrap up the 2006 Fermat paper, and that's actually going to wrap up all the 2006 multiple choice questions. Multiple choice question contests. So what have we got next? The Hypatia, which will be the written contest aimed at grade 11, will be the next thing I go through. Thank you guys as always for watching, and I will see you for more Fermats in the future, more Hypatias coming up, and of course the big one, the Euclid, we still have left to do for 2006. There's lots of stuff, so I will see you guys in future videos. So long.